Welcome to ECE 302. This is lecture A1 on random processes. I'm Professor Stanley Chan. So today we're going to look at a very new topic, which is the topic on random processes. The idea of random processes are generalizations of the random variables. Here we're not just looking at one variable, but we're looking at a function. Random processes are extremely useful when you deal with time series. For example, think about the stock market. It is a time series, and therefore the random processes will be a good model for those events. You can also think about a speech signal. As we speak, the sinusoid waves, they will form a random process. There are many great examples of random processes. And here we're only looking at the most basic elements of random processes. The goal is not to make you become fluent in the subject, but rather we want you to know the ideas of random processes, what are the statistical perspectives of random processes, and what are the linkage with the time processes, meaning that the time average compared to the statistical average. So what are actually random processes? Here is a summary of the random processes. What is a random process? A random process is a function indexed by a random key. Now, this statement is a distillation of many pages of lecture notes into just one sentence. And it would take a while to explain this sentence. At a high level, what do I mean by a random process is that it is a function f and it is a function of t. So what would be a random process? You can think of a sinusoid. You can think of a whatever signal that involves time. So these are two possible functions. Now, if you only have these functions, they are not random processes because there isn't anything random. The randomness of a random process comes with the second part of this sentence. It says that a function has to be indexed by a random key. Now, what is a random key? Here we have two functions. We have function 1, f, t, and then let me call an index, I call it psi1. This is another function f of t. It is indexed by psi2. So here we have two different functions. Each one of those is indexed by a different index. This index can be a random index. You can think of that there is a bag, and inside this bag there are two possible indexes. One is psi1, the other one is psi2. So if you put your hand into the bag, you're going to pull one of the two indexes out with certain probability. Let's say you pick this index, then what you're getting will be this function. If you pick the other index, you will be getting the other function. In this case, the function f of t is no longer a deterministic quantity. You have two random indexes to tell you which of the two functions you're actually drawing from the sample space. And in that case, we say that this function f is a random process, because it is indexed by a random key. Now, of course, in your sample space, if you only have one index, and whatever you draw, it will be index 1, then it is no longer a random process. It becomes a deterministic random process. This is not clear until we look at a few examples, and here's the first one. So suppose we consider the equations of lines we have ft equals to at plus b, where a and b are constants and they are random variables drawn according to certain distribution. The time index t is arranged from -2 to 2. So if I draw a random pair of constants a and b, I will be getting a particular line. For example, I say a equals to this number, b equals to that number, I am going to get this straight line. Tomorrow morning, I'm going to redo this experiment, and then I got another line that corresponds to another pair of a and b. The third day morning, I pick another line, I will get this one. So this is the set of all possible lines I can draw by picking a different pairs of a and b. And note that a and b, they are distributed according to some distribution. And in this case, I say that it is distributed according to a uniform distribution for some ranges of a and b. And so what are the random process? Well, here this function f of t, it is a random process. What are the indexes? Well, there is an index. There is the index of this pair of numbers, a and b. So this set of straight lines, they define a random process. Now note that a random process is the same as a random variable in the sense that it can take many different states. All you need to do is to specify the probability of getting a particular state. In a random process, the probability will be the probability to get a particular function rather than a particular number. So to be more formal, here we're defining this function f of t with an index psi. This psi will determine this pair of constants a and b, and this psi is drawn from certain sample space omega. And so if the sample space contains these two pairs of numbers, 1.2 and 0.6, the other pair is -0.75 and 1.8, and then the probability of getting each pair is 1/2. Then the random process f of t psi is given by these two equations. You have half probability of getting the first one, you have half probability of getting the other one. And therefore f of t of psi is called the random process. Let us look at another example. In this case, the function is defined as cosine omega 0t plus theta. This t, the time index, is ranged from -1 to 1. And then this theta is a random phase and distributed uniformly over the range from 0 to 2 pi. So what are the functions? Well, as you vary this theta, you are going to get this cosine function shift left and right by the amount of theta, because theta is the phase. And since your theta is ranged from 0 to 2 pi, you're basically covering the entire period of this cosine function. So what are the possible realizations of this random process? All these colored lines, they are the realizations of this random process. Whenever you give me a theta, I will be able to give you a function. So to be more formal, what is the random process? I can specify a psi, and then the theta would be a function depending on this random index psi. So as long as I can pick a psi, I will determine the theta, and then once I get the theta, I will get a function. And that is my random process. So here are just two examples. The first example is that we pick a psi 1, and then correspondingly the theta will give me 3 pi over 4. The other example would be I pick a psi 2, And then correspondingly, the theta will give me minus 7 pi over 3. So in either case, I will get a function. But this function has certain probability of happening. It really depends on my choice of theta. So the probability of getting this one is specified by the PDF of theta, and theta is uniform across the range of 0 to 2 pi. And so if I have a bag and I put my hand into the bag, I pull a sample out, this sample would either be would be one of those cosine functions with a different phase. So what is the sample space of random process? When you think about a random variable, you put your hand into the sample space. The thing that you pull out will be a random number. It will be a number. When you talk about random processes and when you put your hand into the bag, you pull a sample out, that sample will be a function. These functions, they are indexed by this, the psi, 1 and 2 and so on. These are called the random indexes. A very important topic of random processes is the difference between the statistical average and also the temporal average. Now, this difference is extremely important because many students, they will mess up between these two concepts. So let me explain clearly what they really mean. For a random process, these two are the two ways of looking at things. The first one is called the temporal average. What does it mean? It means that suppose you have a function that has this kind of shape. You want to calculate the average, and this is the temporal average. So let's say here is your f of t, and then you want to calculate the average. Then the average would be the integration over all the possible t's, because you're integrating horizontally over all the time indexes, and then you divide by 1 over t if you set a range from 0 to t. And that is your temporal average, something that we do all the time. For example, I give you a speech signal, you take the temporal average, that would be it. Okay, and look at this diagram. The way you take the temporal average is to take the average or take the integration horizontally. Now, remember that this is a random process, and so we can also talk about the statistical perspective of this random process. What do I mean by the statistical perspective? Well, you look at every point in this random process. Okay, so of course the x-axis is the time axis, and at every point time t you will be able to get a value. These are the possible values, and now you can look at these values. This is just a particular time t0, for example, right? So this is time t0, and then these functions, they are indexed by a random index. So here it is x of t0 using the index psi1. This is a function using psi2, psi3, psi4. So these are all the random realizations of a random process. And I'm just looking at this time t0, and I'm looking at things vertically. So if you look at things vertically, what do you get? Well, you get this sequence of numbers. Why? Why are they numbers? Because you're looking at a particular time instance, and so they are all just numbers, right? One number here, number here, number here, and number here. They are random numbers, and they are random realizations of a random variable. Why are they variables? Well, because you look at this column of numbers, they have different values, and they have different probability of happening according to your psi 1, 2, 3, and 4. And therefore, if I look at the things vertically, I am going to get a random variable with all these 4 possible states. And in these states, they have different probabilities. And so if I take the average vertically, I am going to take the average of a random variable with 4 different states. So the statistical average says that I am going to look at, for every time t in my time axis, I treat all these columns as random variables. And every time instant, I have a random variable, and if I take the expectation, I will be able to get the statistical average. Now, normally in practice, you don't do this. You don't do the statistical average concept. Most of the time, you're doing this temporal average. However, in random processes, what you really care is indeed the statistical average. Why? Because you will be able to get a particular time series. And if you take the average of that time series over the time, you're just getting the temporal average. You don't know the statistical properties, and you have no way to understand the correlation between samples to samples. And therefore, the only way to calculate the statistical property of a random process is to look at the statistical properties, which is, for example, the statistical average. And in that case, you're really talking about putting all these functions here, and then you look at the average vertically. And that constitutes 2 different views of a random process. One is the horizontal view, which is something that we are very familiar with. The other one is the statistical view, which is a very new concept to many of you. So a little bit more technical details about the statistical view versus the temporal view. If you look at the statistical view, you are fixing a time t, and then you have all these random indexes. And this is a sequence of random variables because the psi1 through psi-n, they are realizations of the random variable psi. If you look at the things horizontally, you're going to fix an index. Basically, you're just picking one function, and then you look at different time indexes with the same key, okay, psi. The psi doesn't change. The only thing that you change is the t1 through tk. In this case, you're getting a deterministic function, and if you take the average, you're getting the average of this deterministic function. So let's look at a few examples to make sure that we understand the difference between the statistical view and also the temporal view. Let's say I have a random variable a, which is drawn from a uniform distribution from 0 to 1. And then you have this random process defined as a, and then cosine 2 pi t. And here, to be more explicit, I put a psi with the a to denote that this a, this amplitude, is a random variable drawn according to the uniform distribution. So if I look at the statistical view, I can say, for example, time t equals to 10. And in that case, we can show that this x of t with psi, then I am looking at what? Well, I'm looking at this cosine function with t equals to 10. So I have cosine of 20 pi. What is cosine 20 pi? Well, it's just a number. It's a fixed number. And then what is this? This thing here is the a of psi. That is the random variable. So what it becomes is that psi of t and psi, okay, x of t and psi, and now I replace the t with 10. Then what do I have? I can show that this becomes a psi of cosine 20 pi. I can ignore this 20 pi because it's just a number. Okay, so it's a constant. It doesn't change. It doesn't have any randomness. And so this random function is evaluated at 10. That equals to a random variable. That explains why, when I say that this statistical view, this thing here is a random variable. If you look at a particular time t, you are getting a random variable. You go to another time instance, let's say x at 15, you are getting another random variable. These two random variables, they may be correlated, but literally speaking, they are just two random variables. There are two random variables. They could be correlated, they could be dependent, but they are random variables by their own. That is the statistical view. When you write down this function, x of t psi equals to a cosine 2 pi t, that is giving you a random variable when you plug t equals to a particular number. Now, the temporal view is different. The temporal view says that you need to fix a psi. And once you fix a psi, what does it mean? Well, let's say you pick a psi and the a psi equals to 0.7. That is equivalent to saying that I put my hand into a bag and then put a number out, and this is 0.7. And then this bag contains all the uniformly distributed numbers from 0 to 1. And so I have already picked this a equals to 0.7 with certain probability, of course. Now, once you have picked this a, what do you have? This x of t psi equals to 0.7 times cosine 2 pi t. There is no randomness in this function. It is just a cosine function that changes over the time t. There is nothing random. No matter how you take the expectation, you take the statistical averages, it's not going to change anything. It will just become a function in time. There is nothing random because you have already picked this a to be a number. The pictorial illustration of this example is shown here. You have random realizations of this a cosine 2 pi t function. The horizontal axis is the time axis. It's a function of t. The vertical axis is this number a cosine 2 pi t. For different choices of a, you are getting a different cosine function. However, since there's no phase offset, you're always getting the same shape of the cosine function with a different amplitude. For example, here, x1, this is your x1. It is the smallest amplitude random realization. You can even get smaller. It depends on what a that you're drawing. It could be that a equals to 0. That could happen. Now, if that happens, you just get a constant 0. All these lines in this plot, they represent the realizations of this random process, a cosine 2 pi t. By flipping a different a, I am getting a different random process. Let's look at another example. In this example, I consider a discrete random variable a. This discrete random variable has two states, +1 and -1. The probability of getting +1 is half. The other one is also half. And then I define this random process. This random process has that I have the random index psi, and then I have the time index n. And it is defined as -1 to the power n with this amplitude a psi. But a, of course, it would be either +1 or -1. So what do you have? Well, you have only two choices of functions. Depends on the state of your a. Your a can be a +1, your a can be a -1. If it's +1, and then you have -1 to the power n, and then -1 to the power n, that will just give you -1 to the power n. Now, if you have -1 here, then you have -1 to the power m -1, m plus 1. Okay, so this random process has two possible states. It would be either this sequence or that sequence. The probability of getting those would be 1/2 and 1/2. So if you fix your time n equals to 10, let's say, then your function x evaluated at 10 with this random index psi will be either +1 or -1 with probability 1/2 and 1/2. And therefore this quantity here, it is a random variable with two states. The temporal view says that I am going to fix a psi. So among these two functions, I'm going to pick one function or the other function. And then if I pick this function, then what will it become? Well, it will just become this function is a time series. If I pick the other one, I will have another time series. There's nothing random in this case. So how do these two functions look like? These two functions look like this one. You have either you start with +1 and then go to -1, you oscillate between the two, or you start with -1 and go to +1 again. These two are the two possible choices of functions in your sample space. You can ask, is it possible to get a random process x of n equals to -1, -1, +1, +1, etc. This is not possible, okay? Not possible, because this function does not belong to the sample space. You will have 0 probability of getting this one. Okay, there's half probability of getting this time series. You have half probability getting the other time series. So, to summarize, what have we learned in this section? Well, in this lecture, we have discussed the basic ideas of random processes. The most important things to remember in a random process is that the sample space is now no longer just containing random numbers. Now each sample is a random function. And since you're drawing a random function, you can talk about its randomness. The randomness associated with a random function goes with the random index. For different index, I will draw a different function. However, at every time t, so if I fix a time t here, and then I look at the things vertically, I am going to get a random variable. If I go to another time t here, I'm going to get another random variable. And therefore, the random process can be thought as an infinite sequence of random variables stacked together. In what sense? Well, you have x, you have t1, you have psi. You have x at t2, you have psi. All these, they form a sequence of random variables. And we can talk about the probability of getting this sequence of random variables. Now note that all these sides, they are the same, and therefore we can talk about the probability of getting the entire sequence. The two views are very, very important. The first one is the statistical average. It says that I'm going to take the average of this t of psi vertically. Okay. The other one is the temporal average, which is to take the average horizontally. In general, statistical average and temporal average, they are different. Only for a very small class of random processes, these two will become the same. And those are the good random processes that allows many practical engineering applications. We will go there in a few lectures. So this is the end of today's lecture. We have introduced the idea of random processes, and then we have introduced the difference between statistical average and also the temporal average. I hope you can spend some time to understand the difference between these two. If you have any question, I welcome you to send an email to me. Most of the discussions can be found in our ebook. Thank you for listening. I hope to see you again next time.